Not every galaxy announces itself with light. Dragonfly 44 sits out past the edge of easy observation, an object with the mass of the Milky Way and almost nothing to show for it. No bright disk, no visible spiral arm, barely a smudge on the best images available. For years, nobody thought to look closely at objects like this, because there was nothing bright enough to draw attention. Then someone built a telescope out of camera lenses and looked anyway. What they found about the dark matter hiding inside Dragonfly 44 forced a rewrite of how astronomers think about galaxies that barely exist to the eye, and started a disagreement that is still running today. Look at Dragonfly 44 through an ordinary telescope and you will not find it. Not because it is too far away. Plenty of things at that distance show up just fine. You will not find it because there is almost nothing there to catch. No sharp core, no bright spiral, just a faint smear most instruments read as noise and throw out. That alone should tell you something is off. A galaxy carrying the mass of the Milky Way does not usually look like this. Mass pulls things together. It compresses gas. It lights up stars. It builds the kind of structure a camera catches without trying. Dragonfly 44 skipped almost all of that. There is a second problem, and honestly, this one bothered the astronomers more than the missing light did. Dragonfly 44 sits inside the Coma Cluster. Thousands of galaxies crowded together there, all pulling on each other hard. Something this thin does not usually last long in a place like that. The pull from its neighbors should stretch it out and pick it apart over time. Something with almost no visible structure, sitting in one of the roughest gravitational neighborhoods nearby, should not still be in one piece. But it is. Which leaves two options. Either we have something wrong about how galaxies get torn apart in crowded clusters, or Dragonfly 44 is holding onto something we cannot see. Think about a boat anchored in a river with a strong current pulling at it. From the surface, all you see is the boat sitting still, calm, steady, like the current is not even there. But the reason it holds is underwater, a length of chain running down to an anchor buried in the riverbed, doing all the actual work while staying completely out of sight. Cut that chain, even partway, and the current stops pretending to be gentle. The boat drifts. Fast. A galaxy inside a cluster is dealing with something similar. The pull comes from outside, from every heavy neighbor nearby, not from anything the galaxy is doing itself. To stay put, it needs enough mass, holding on in the right place, to outmatch that pull. Dragonfly 44 does not have that mass in its stars. If it has it at all, it is somewhere we cannot photograph. The same way you cannot photograph an anchor chain from a boat deck at night. You cannot photograph hidden mass. You can only watch what it does. And the thing astronomers watch, the thing that has worked for close to a century now, is motion. Stars circling a galaxy's center move at a speed set by how much mass is pulling on them. Clock that speed. Work backward. You get the mass, whether you can see it or not. Back in the 1930s, Fritz Zwicky was watching galaxies inside a distant cluster and found them moving far too fast for the visible matter he could account for. Decades later, Vera Rubin tracked the rotation of spiral galaxies and kept running into the same gap, galaxy after galaxy, no matter where she looked. Neither one of them went looking for some new kind of matter. They were just doing careful, patient work, and the numbers kept refusing to add up the ordinary way. We bring that up here because what happened to Dragonfly 44 decades later is not some strange exception to their work. It is the same question, asked again, on something extreme enough that the answer got hard to argue with. A normal spiral galaxy carries a lot of visible material. Stars, gas, dust, all of it adding weight to the total, all of it making the measurement messier. A galaxy like Dragonfly 44 clears most of that mess away. Whatever mass is moving those stars has almost nowhere else to hide. That is why a small team of astronomers looked twice at this particular smudge of light when most people would have kept scrolling past it. Not because it was beautiful. It is not. Not because it was bright. It barely registers. They looked because it was close to the opposite of both, and that emptiness turned out to be the whole reason it mattered. Every galaxy we have measured closely enough has turned out to carry more mass than its visible matter explains. That is not some rare oddball result. It is close to the rule. What makes Dragonfly 44 different is not that it hides mass. Almost everything does, one way or another. What makes it different is how much and how little visible material is left standing to argue with. So the question in front of us is not really whether something invisible is holding this galaxy together. That much, across thousands of galaxies, is about as solid a finding as astronomy has to offer. The real question is how much of it lives inside this one object, and whether the answer would end up matching what everyone expected or knock it sideways. Getting that answer meant somebody had to find a way to look closely at something this faint. The tool that made it possible did not come out of a billion-dollar observatory. It came from something a lot stranger than that. There is a detail about big telescopes that most people never think to ask about, and it turns out to sit at the center of why Dragonfly 44 stayed invisible for as long as it did. The mirrors and lenses inside a professional telescope are enormous, ground to a precision measured in fractions of a wavelength of light, built to gather as many photons as possible from something faint and far away. That serves you well if you are looking at a distant point of light, a single star, a compact galaxy core, anything with a sharp edge and a clear center. But that same design works against you if what you are chasing is something spread out thin across a wide patch of sky. Here is the mechanism. Inside a big telescope, light does not travel in one clean, uninterrupted path from the sky to the sensor. It bounces. It reflects, faintly, off the inner edges of the optical tube, off the support structures holding the mirrors in place, off tiny imperfections in the glass itself. Most of that scattered light stays so weak compared to the bright object you are studying that you never notice it. But when the object you are studying carries almost no brightness of its own, when it sits closer to the glow of the night sky itself, that faint internal scattering stops being invisible. It turns into noise loud enough to bury the signal you are trying to find. Picture listening for a whisper in a room where a fan runs quietly in the background. If the person speaking is shouting, the fan makes no difference. You hear them fine. But if they are whispering, that same quiet fan noise, the one you barely registered a moment ago, becomes the entire obstacle. Dragonfly 44 is a whisper. Most of the largest telescopes on Earth, for all their power, were built with fans running in the background that nobody had ever needed to silence before. Two astronomers set out to solve exactly this, not by building something bigger, but by building something almost embarrassingly simple. Peter van Dokkum at Yale and Roberto Abraham at the University of Toronto had both spent years working with conventional telescopes, and both had run into the same wall, images of the sky that looked clean everywhere except in the faint, diffuse regions where scattered light from bright stars nearby smeared everything into a haze. Rather than fight that problem with a bigger mirror, they asked a different question. What if the tool itself already existed, engineered cheaply, at scale, for a purpose that had nothing to do with astronomy? The answer they landed on was a camera lens, not a telescope lens. A telephoto camera lens, the kind used in commercial photography, coated with a nanostructure designed specifically to suppress internal reflections almost completely. That coating exists for a much more ordinary reason than astronomy. Shoot a photograph into bright sunlight or toward a stage light, and internal lens reflections show up as ghost images and hazy flares ruining the shot. Camera manufacturers spent years refining coatings to kill that problem for wedding photographers and sports photographers who never once thought about ultra-diffuse galaxies. Van Dockum and Abraham recognized that the same coating, built to protect a wedding photo from a stray flare, solved almost exactly the obstacle blocking astronomers from seeing extremely faint, extremely spread-out light in the sky. So they did something no serious observatory had tried before. They bought a set of these lenses, mounted several side by side on a single tracking frame, and pointed the whole array at the same patch of sky at once. This matters scientifically, not just practically. A single lens, however well coated, only gathers a certain amount of light. Align several lenses on the same target and combine their images together digitally, and the faint signal you are hunting for adds up consistently across every lens, while the random noise in each individual image tends to cancel out when you stack them. The result behaves almost like one much larger, custom-built telescope, purpose-designed to be almost completely blind to the specific kind of internal scattering that had been hiding objects like Dragonfly 44 in plain sight for decades. They called it the Dragonfly telephoto array. There is something to sit with in how strange that origin story is inside the history of astronomy. Most instruments capable of a genuine breakthrough get built with enormous budgets, purpose-engineered optics, years of specialized fabrication. This one started with equipment you could, in principle, walk into a camera store and buy off a shelf. That does not diminish what Van Dockum and Abraham accomplished. If anything, it sharpens it. They spotted a mismatch between what conventional telescopes were optimized for and what a specific class of astronomical object actually needed, and instead of assuming bigger was always better, they went looking in an unlikely place for the exact property that mattered. Progress in astronomy usually gets told as a story of bigger mirrors and higher budgets, each new observatory outdoing the last in raw size. Van Dockum and Abraham's approach cuts directly against that assumption. The right question, asked carefully, sometimes matters more than the biggest hardware in the room. When they pointed this new array at the Coma Cluster, patches of sky already photographed many times before by far larger telescopes, they were not expecting to find anything new about objects everyone already knew existed. They were testing whether their instrument worked as intended. And in those images, sitting where astronomers had looked many times before, there were faint, extended, low surface brightness patches nobody had properly cataloged, objects too diffuse for the scattered light of conventional telescopes to resolve clearly. Dragonfly 44 was one of those patches. This was not a galaxy hiding at the far edge of observable space, too distant for anyone to have reached it before. It sat inside one of the most heavily studied clusters in the sky, close enough and large enough that it should have been obvious. Nobody had simply looked at it with an instrument quiet enough to notice it. That raises a real question about how much else might be sitting in plain sight right now, hiding not from distance, but from the absence of the right kind of quiet instrument to hear it. Finding a smudge of light in an image only gets you to step one. Recognizing that something is there does not tell you what it actually is, how much mass it holds, or whether it is even a coherent galaxy, rather than some trick of foreground scattering the new instrument itself might be producing. Answering that meant pointing a completely different kind of instrument at this same faint smudge, one built not to gather light, but to measure exactly how fast the stars inside it were moving. And what that measurement returned took the story from an interesting discovery to something that genuinely unsettled people. A picture on a screen can tell you that something is there. It cannot tell you how much it weighs. That gap between seeing a shape and knowing its mass is exactly where the Dragonfly telephoto array had to stop and hand the problem to a completely different instrument. To close that gap, Peter van Dokkum and his colleagues needed to measure something the camera lenses were never built to capture. Not light, motion. Specifically, the speed at which stars inside Dragonfly 44 were moving around its center. That number, once you have it, tells you almost everything about how much mass is holding those stars in orbit, whether you can see that mass or not. Here is the mechanism behind that, and it rests on something you have probably felt without ever thinking about the physics of it. When an ambulance passes you on the street, the pitch of the siren shifts, higher as it approaches, lower as it pulls away. That shift happens because sound waves compress slightly when their source moves toward you, and stretch slightly when it moves away. Light behaves the same way. When a star moves toward us, the light it gives off shifts very slightly toward bluer wavelengths. When it moves away, that light shifts toward redder wavelengths. Astronomers call this a Doppler shift, and it lets them do something remarkable from hundreds of millions of light years away. By spreading a star's light out into a spectrum and measuring exactly how much that spectrum has shifted, they can calculate precisely how fast that star is moving toward us or away from us. Do this for enough stars scattered across a galaxy, and you get a map of motion. Faster orbital speeds mean more mass is pulling on those stars. Slower speeds mean less. This sounds simple stated that way. In practice, applying it to a galaxy as faint as Dragonfly 44 is one of the more demanding measurements in modern astronomy. A bright, dense galaxy gives you plenty of starlight to spread into a spectrum and analyze quickly. Dragonfly 44 gives you almost nothing. Its light is so thin, so spread out, that pulling a clean, usable spectrum out of it takes an extraordinary amount of collected light, gathered patiently, over a long stretch of time. This is where the instrument called DEIMOS comes into the story, mounted on the Keck 2 telescope in Hawaii, one of the largest optical telescopes on Earth. DEIMOS was designed specifically for this kind of work, spreading starlight into detailed spectra so faint signals can still be measured accurately. Even with an instrument this capable, pulling a reliable velocity measurement out of Dragonfly 44 required pointing at the same patch of sky night after night and simply waiting. Van Dokkum and his team spent 33.5 hours collecting light from this one galaxy, spread across 6 separate nights. Think about what that actually means in practice. 6 nights where the telescope time, some of the most competitively requested resource in modern astronomy, went entirely toward one faint, unglamorous smear of light that most observers would have skipped over without a second look. No guarantee, going in, that the data would even resolve into something usable. Science at this level often looks less like a flash of discovery and more like a long, uncertain wait for a signal that might not show up clearly, no matter how carefully you gather it. We think that patience is worth pausing on, not to romanticize it, but because it changes how you should picture this moment. This was not one dramatic night at the eyepiece. It was 6 nights, spread out, each one adding a little more signal, a little more confidence, with no way to know until the very end whether the final result would be strong enough to publish anything at all. When the data finally came together, it produced something called a velocity dispersion, a measurement of how much the speeds of individual stars inside the galaxy varied from the average. A tight, narrow spread of velocities suggests a small amount of mass holding things together gently. A wide spread suggests something much heavier is pulling those stars around at a wide range of speeds, the way a fast, tight orbit around a massive object produces a different kind of motion than a slow, loose orbit around something lighter. The velocity dispersion Van Dokkum's team measured in Dragonfly 44 came back high, not moderately high. High enough that, when they ran the numbers forward into an estimate of mass, The total came out close to 1,000,000,000,000 times the mass of our Sun, roughly comparable to the entire mass of the Milky Way. Sit with that pairing for a second, because it is the heart of everything that followed. A galaxy giving off roughly 1% of the light of the Milky Way, showing a mass close to matching it. That is not a small discrepancy you could explain away with measurement error or an unusual viewing angle. That is a gap wide enough to demand an explanation, and there were only a few candidates on the table. Either the measurement was wrong in some way not yet understood, or the stars themselves were somehow behaving in a way nobody expected, or there was a huge quantity of mass inside Dragonfly 44 that gave off no light at all. Van Dokkum and his colleagues did not rush to the most dramatic of those three explanations. They checked their instruments. They cross-checked their calculations. They considered whether foreground contamination, light from unrelated stars along the same line of sight, could have inflated the result. None of those alternative explanations held up cleanly against the data. What remained, after ruling out the ordinary sources of error, was the possibility that had seemed the least comfortable to accept when the observing run started. Dragonfly 44 appeared to be carrying an enormous amount of mass that was not made of stars, not made of anything glowing brightly enough to register in an ordinary image. And there was one more independent line of evidence sitting in the same dataset, something that had nothing to do with the velocity measurement at all, that pointed in exactly the same direction. The second piece of evidence had nothing to do with velocity, and it came from a much simpler kind of observation, just counting. While Van Dokkum's team was measuring how fast individual stars moved inside Dragonfly 44, another instrument, the Gemini Multi-Object Spectrograph on the 8-meter Gemini North Telescope in Hawaii, was being used to look for something different scattered around the galaxy's outer regions: globular clusters. If you have never come across the term, a globular cluster is a tight, roughly spherical ball of stars, sometimes hundreds of thousands of them, bound together by their own gravity, orbiting a larger galaxy the way a moon orbits a planet. The Milky Way has around 150 of them, ancient structures, some nearly as old as the universe itself, drifting slowly around our galaxy's outskirts. Here is why counting them matters, and it comes from a pattern astronomers have confirmed across a huge range of galaxies over decades of observation. The number of globular clusters orbiting a galaxy tends to scale with that galaxy's total mass, not its brightness, not its visible size, its mass. A small, low-mass galaxy might have a handful of globular clusters. A galaxy the size of the Milky Way has around 150. The relationship is not exact, but it is consistent enough that astronomers use it as a rough, independent gauge of how much a galaxy actually weighs, separate from anything you can measure by watching stars move. When the Gemini team counted the globular clusters around Dragonfly 44, they found somewhere close to 90 of them. 90. Orbiting a galaxy so faint that most sky surveys had passed right over it. That number sits in the same range you would expect from a galaxy with the mass of the Milky Way, not a galaxy with 1% of its light. Two completely different instruments, measuring two completely different things, using two completely different physical principles, arrived at the same conclusion independently. One team measured the speed of starlight shifting across the spectrum. Another team simply counted small, dense balls of stars scattered in the dark around a galaxy's edge. Neither measurement depended on the other. Neither could have been contaminated by the same kind of error. Think about what it means when two unrelated methods, built on unrelated physics, land on the same number. If a single measurement gives you a surprising result, you check your instruments, you check your assumptions, you look for something you might have missed. When a second, independent measurement, using an entirely different technique, arrives at a consistent answer, that is a different situation. That is the kind of agreement that is difficult to explain away as coincidence or error. We find this detail genuinely remarkable, and not because it settles the question of what dark matter actually is. It does not. What it does is something narrower and, in some ways, more convincing. It confirms that whatever is happening inside Dragonfly 44 is not an artifact of one measurement technique or one team's particular instrument. So, by the time these two results sat next to each other in the summer of 2016, the picture had solidified into something hard to dismiss. A galaxy giving off roughly 1% of the light of the Milky Way. A velocity measurement suggesting a mass close to matching it. A globular cluster count landing in the same range you would expect from a galaxy of that mass. 3 separate observations pointing the same direction. Peter van Dokkum described the imbalance this way when the findings were published, noting that there had to be a huge discrepancy between the light coming from the galaxy and the actual mass holding it together, with almost all of that mass located somewhere other than in the stars themselves. That is not a dramatic overstatement. It is close to the plainest possible description of what the data showed. Dark matter dominating a galaxy's mass is not on its own a surprising discovery anymore. It has been the expected result for decades. What made Dragonfly 44 different was not that it had dark matter. What made it different was how extreme the ratio turned out to be, and how useful that extremity made the galaxy for studying dark matter directly, without the usual clutter of stars and gas complicating the picture. Van Dokkum's team put a number on that extremity, and the number is worth hearing plainly rather than glossing over. Based on their original measurements, they estimated that Dragonfly 44 was somewhere in the range of 99.99% dark matter. Take a moment with that fraction. Out of everything holding this galaxy together, everything giving it enough mass to survive inside one of the roughest gravitational neighborhoods nearby, less than 1 part in 10,000 was made of the ordinary matter that makes up stars, planets, and everything you have ever touched. That number turned Dragonfly 44 from an interesting oddity into something astronomers wanted to study very closely. Because if a galaxy exists that is made almost entirely of an invisible substance, with just enough ordinary matter sprinkled through it to give off a faint trace of light, then studying that galaxy means studying dark matter itself, with far less interference than any ordinary galaxy could offer. But a number this extreme, published in a single set of measurements, was never going to be the final word. Science does not work that way, and it should not. A result, this striking, invites exactly the kind of scrutiny it eventually received, from a different team, using a more precise instrument, several years later. And what they found did not simply confirm the original picture. 3 years after the first measurement, a new instrument came online at Keck Observatory, one built to do something the earlier equipment could not. Instead of collecting light from a galaxy as a single blended signal, the Keck Cosmic Web Imager could break that light apart across many small regions at once, building something closer to a detailed map than a single number. Van Dokkum's team pointed it back at Dragonfly 44. This was not a routine follow-up. Redoing a measurement that had already made headlines, using a more capable instrument, carries a real risk for the people running the study. If the new numbers match the old ones, that would be reassuring but not especially newsworthy. If they did not match, the team would have to explain, in public, why their own earlier work needed correcting. They ran the observation anyway. 25 hours of data collection, spread across the Keck Cosmic Web Imager's field of view, resolving motion star cluster by star cluster, rather than averaging the whole galaxy into one blended reading. The result came back lower, not by a small amount. The velocity dispersion, the same quantity that had driven the original trillion solar mass estimate, measured out at roughly 33 kilometers per second across the galaxy's central region, meaningfully below what the earlier Deimos measurement had suggested. Velocity dispersion does not scale directly with mass. It scales with something closer to the square root of mass. That means a modest-looking drop in the measured velocity can translate into a much larger drop in the mass estimate built on top of it. When Van Dokkum's team ran the new numbers through, the revised mass came out roughly 6 times lower than their original estimate, closer to 160 billion solar masses rather than the full trillion first reported. Picture 2 rulers measuring the same object, one calibrated in a way that magnifies small reading errors into large size differences. A tiny shift in where you place the ruler produces a big shift in the number you write down. Velocity dispersion behaves something like that ruler in relation to mass. A small change in the speed you measure can swing the mass estimate by a wide margin. That is not a flaw in the method. It is simply the shape of the relationship, and it explains why a measurement this delicate benefits enormously from a second, more precise look. None of this erased the original finding entirely. Dragonfly 44 still carried far more mass than its visible stars could account for. The revised numbers still pointed toward a galaxy dominated by something unseen. What changed was the scale of that imbalance, and the confidence with which anyone could call this particular galaxy a near-perfect stand-in for the Milky Way's mass. A team publicly revised its own headline result, using better data, and said so plainly. That is not a story about scientists getting it wrong. It is a story about how a correct scientific process actually looks from the inside. Uncertain in the beginning, refined through better instruments, willing to say the earlier number needs adjusting once stronger evidence exists. Not everyone in the field read the revision the same way. Some researchers who had spent years questioning whether dark matter was the right explanation at all saw the lower number as support for a different idea entirely, one that does not require invisible mass to explain how galaxies move. That disagreement did not start with Dragonfly 44, and it did not end there either. Every measurement in this story so far has assumed one thing without saying it directly: that the extra mass pulling on Dragonfly 44's stars is real matter, just matter that does not glow, something physical, sitting there, contributing weight the way any object contributes weight, only invisible to every instrument built to detect light. That assumption has a name: dark matter, and it is worth being honest about something most explanations skip past. Nobody has ever directly detected a particle of it. This is not a small caveat. Decades of experiments, buried deep underground to shield out cosmic radiation, built specifically to catch a dark matter particle, interacting with ordinary matter even once, have come back empty. The evidence for dark matter is overwhelming when you look at how galaxies move, how clusters hold together, how light bends around massive structures. But every single piece of that evidence is indirect. We infer the mass from its gravitational effects. We have never held the thing itself. A small number of physicists have spent decades asking whether that gap matters more than most people assume. Their question is not whether something strange is happening inside galaxies like Dragonfly 44. Everyone agrees something strange is happening. Their question is whether the explanation has to be invisible matter at all, or whether gravity itself behaves slightly differently than Newton and Einstein described. Once you get to the extremely weak gravitational pull found at a galaxy's outer edge. This idea is called modified Newtonian dynamics, usually shortened to MOND. Instead of adding invisible mass to make the numbers work, MOND changes the equation for gravity itself at very low accelerations. Under this framework, stars at a galaxy's edge move faster than Newton's law predicts, not because something unseen is pulling on them, but because gravity stops following the familiar rule once the pull gets weak enough. Think about how a simple rule can hold up well in the conditions where you first tested it, and then quietly break down somewhere you never checked. A thermometer calibrated against boiling water and ice works beautifully across the range most people ever use it for. Push it toward the extreme edges of temperature, and it starts giving readings nobody would trust. That does not mean the thermometer is useless. It means every measuring tool, including a law of physics, carries an implicit range where it has actually been tested. MOND asks whether Newtonian and Einsteinian gravity have simply never been tested carefully enough at the extremely weak end, the exact end where galaxy rotation curves live. For most of the last 40 years, dark matter has had a decisive advantage over MOND, because dark matter explains far more than just galaxy rotation. It explains the way clusters of galaxies bend light through gravitational lensing. It explains the pattern of the earliest light in the universe, the cosmic microwave background. It explains how galaxies clumped together in the first place, billions of years ago. MOND, in its original form, struggles badly with several of these. Modifying gravity to fix rotation curves does not automatically fix the bending of light around galaxy clusters, and several attempts to extend MOND into a fuller theory have run into serious trouble matching that evidence. So why does the debate persist at all, instead of settling cleanly in dark matter's favor? Because Dragonfly 44's own revised numbers, the lower velocity dispersion measured in 2019 landed closer to what MOND would predict for a galaxy with that little visible mass than some dark matter models expected. Researchers who favor MOND pointed to that agreement directly. Stacy McGaugh, one of the more prominent voices arguing for modified gravity, described the shift in Dragonfly 44's measured rotation speed as an example of the data evolving toward what MOND had predicted all along. One galaxy's revised measurement does not overturn 40 years of accumulated evidence for dark matter. Most astronomers who work in this field still consider dark matter the far stronger explanation, supported by a much wider range of independent evidence than any single galaxy could provide. But most astronomers in this field also acknowledge, when pressed honestly, that the agreement is not total. There is no experiment yet that has closed this question completely in either direction. We think that is worth sitting with for a moment, not because it makes the science shaky, but because it shows what real science actually looks like while it is still being worked out. Two serious explanations, each backed by careful researchers, each pointing to real data, disagreeing about how to interpret the same galaxy. That is a very different picture than the one most documentaries give you, where a question gets asked and then answered cleanly within the same episode. This one has not been answered cleanly. Not yet. What makes Dragonfly 44 such a useful test case for either side of this argument comes back to the same property that made it useful in the first place. It has almost no visible matter cluttering the picture. Whatever gravitational story is unfolding inside it, dark matter or modified gravity plays out with less interference from ordinary stars and gas than in almost any other galaxy astronomers have access to. That is exactly why researchers on both sides keep returning to this same faint smudge of light in the Coma Cluster, hoping the next measurement with the next generation of instruments will finally tip the balance one way or the other. It has not tipped yet, and there is a deeper question sitting underneath this entire disagreement, one that goes beyond Dragonfly 44 entirely. If a galaxy this extreme cannot settle the argument between dark matter and modified gravity, what would it actually take to settle it? If two explanations disagree about a galaxy's hidden mass, and neither velocity measurements nor globular cluster counts can settle it, you need a third method, one that does not depend on watching stars move at all. That method came from something you would not expect to help here: X-rays. Here is the reasoning behind it, and it starts from a fact about galaxies that has nothing to do with dark matter directly. Galaxies sitting inside dense clusters often carry a thin haze of hot gas around them, heated by their own gravitational environment to temperatures high enough to glow faintly in X-ray light. The more massive a galaxy's dark matter halo, the more strongly it holds onto that hot gas, and generally the more X-ray emission you expect to detect coming from it. If Dragonfly 44 really does sit inside a massive dark matter halo, something roughly comparable to the Milky Way's, that halo should leave a faint X-ray signature astronomers can look for directly. Think of it the way a large lake retains heat long after sunset, while a shallow puddle cools almost immediately. The lake's greater volume holds on to thermal energy longer, and you can measure that retained heat without ever watching the water itself move. A massive dark matter halo works on a similar logic for hot gas. More mass means a deeper gravitational well, and a deeper well holds gas at higher temperatures for longer, which shows up as X-ray light. Look for that light, and you get an estimate of the halo's mass built on physics that has nothing to do with stellar velocity or globular cluster counts. A researcher named Akos Bogdan took on exactly this test, pointing two of the most capable X-ray observatories available, Chandra and XMM Newton, directly at Dragonfly 44. If the original estimate was right, if this galaxy really carried a dark matter halo massive enough to rival the Milky Way, there should have been a detectable glow of hot gas surrounding it. There was none. Not a faint trace, not an ambiguous signal buried in noise. The X-ray observations came back essentially empty, and that emptiness set a hard upper limit on how massive Dragonfly 44's dark matter halo could realistically be, a limit well below what the original velocity-based estimate had suggested. An absence of X-ray light does not prove dark matter is the wrong explanation. It does not prove Dragonfly 44 has no dark matter at all. What it does is narrow the range of possibilities. Based on this evidence, Bogdan argued that Dragonfly 44 likely does not sit inside a halo as massive as the original trillion solar mass figure implied. Instead, the X-ray limits point toward a galaxy more consistent, with a smaller, dwarf galaxy-scale halo, something closer to other faint galaxies of its kind, rather than a true dark twin of the Milky Way. Notice what just happened across three completely different techniques. Velocity measurements gave one estimate, then a revised, lower estimate. Globular cluster counts suggested a Milky Way scale mass. X-ray observations pointed towards something considerably smaller. Three independent methods, three different numbers, none of them agreeing cleanly with each other. We think this disagreement matters more than any single measurement in this whole story, because it shows you something science rarely gets credit for showing openly. Real scientific evidence does not always converge neatly. Sometimes it produces a genuine tension between methods, each one sound on its own terms, each one telling you something true about a different piece of the puzzle without adding up to one tidy answer. This is not a flaw in the process. It is what an honest, ongoing investigation actually looks like from the inside, before the story gets simplified for a textbook years later. Dragonfly 44 has not settled into a single, agreed-upon mass. It has become something closer to a live case file, one astronomers keep returning to, each new instrument adding another data point rather than a final verdict. Which raises a question that goes beyond just this one galaxy. If a decade of careful, independent measurement from four separate instruments can produce a hard disagreement instead of a clean number, what does that tell us about the other few thousand ultra-diffuse galaxies scattered across the sky, the ones nobody has spent this much time and telescope hours on yet? Four independent techniques, and still no single number everyone agrees on for Dragonfly 44's true mass. Before going further, it helps to ask a plain question. Why does a disagreement like this not embarrass the scientists involved? Consider what actually happened here. A team measured a galaxy's velocity in 2016 and published a striking result. Another instrument, 3 years later, gave a lower number. A separate team pointed X-ray telescopes at the same galaxy and found evidence for something smaller still. None of these results contradicts the others in a way that suggests a mistake. Each one measured something slightly different, under different assumptions, with different sources of possible error. Picture 4 people trying to estimate the depth of a lake using different tools. One drops a weighted line and counts how much rope goes out before it goes slack. Another uses sonar, bouncing sound off the bottom and timing the return. A third studies how quickly the water near the shore cools at night, since deeper water holds heat longer. A fourth watches how strongly the lake pulls a small boat off course in a crosswind, since a deeper, larger body of water exerts different drag than a shallow one. All four methods are sound. All four are measuring the same lake. And yet each one carries its own blind spot, its own margin of error, its own set of conditions where it works best and conditions where it struggles. If their numbers come back close but not identical, that does not mean someone measured wrong. It means each tool is telling you something true about a different slice of the same reality. Return to Dragonfly 44 with that in mind. Velocity dispersion measures the motion of stars in a specific inner region, and that motion depends heavily on exactly which stars you manage to capture in your observation, and how sensitive your instrument is to fast versus slow-moving ones. Globular cluster counts depend on an empirical relationship built from studying other galaxies, one that holds up well on average but was never guaranteed to apply perfectly to any single unusual case. X-ray emission depends on whether a galaxy's hot gas halo survived intact or whether it was stripped away by the crowded, violent environment of the Coma Cluster long before anyone thought to look for it. Each method carries an assumption baked into it. Each assumption can fail quietly, in ways that only show up when you compare the result against a completely different technique. The scientists working on Dragonfly 44 did not treat the disagreement between methods as a crisis to hide. They published it. Peter van Dokkum's team put their own revised, lower velocity measurement into the public record in 2019, openly noting that it sat below their original figure. Akos Bogdan published X-ray results that pointed toward an even smaller halo, directly at odds with the original headline number from 3 years earlier. Nobody involved tried to make the numbers agree by adjusting them after the fact. Nobody quietly buried the inconvenient result. The disagreement itself became part of the published scientific record, available for anyone in the field to examine, argue with, and build on. That transparency is not a small thing. Science does not earn trust by always being right on the first attempt. It earns trust by showing its work, including the parts where the work contradicts itself, and by trusting the field to sort out which explanation survives further scrutiny. A result that gets revised in public, with the revision clearly documented, is not a failure of the scientific process. It is that process functioning exactly as intended. Peter van Dokkum built his career, in part, on the original 2016 result. Headlines ran with it. Interviews were given. And 3 years later, his own team's more precise instrument produced a number that complicated that same headline. He published it anyway, under his own name, in the same academic record as the original claim. That is a different kind of integrity than simply being right the first time. It is the willingness to let better evidence overrule your own earlier conclusion in front of your peers, without waiting for someone else to force the correction. We think that deserves to be said plainly. People tend to imagine scientific facts as fixed points, discovered once and then simply known forever. Dragonfly 44 shows something closer to what research actually looks like while it is still active. A number gets measured. A better instrument comes along. The number shifts. The explanation gets debated. Nobody involved treats that shifting as embarrassing, because the alternative, freezing a result in place simply to avoid looking uncertain, would be far worse for anyone trying to understand what is actually true. This also explains something about why Dragonfly 44 keeps drawing attention from researchers on very different sides of the dark matter debate. A settled, uncontested result would not be nearly as useful to study further. An unsettled one, with real tension between independent methods, is exactly the kind of case that forces a field to sharpen its instruments and its assumptions. Every one of the 4 measurements described so far exists because someone was still not satisfied with the number that came before it. That dissatisfaction, that refusal to let an interesting result sit unexamined, is what pushed the story past the question of how much mass Dragonfly 44 carries and into a much harder question. Not what is it made of, but how did it get this way in the first place? Because a galaxy this thin, this faint, sitting in one of the roughest gravitational neighborhoods nearby, did not start out looking like this. Something happened to it, sometime in its history, that left it in the strange, half-formed state astronomers keep arguing about today. A galaxy this thin did not arrive in the universe looking like this. Something happened, somewhere in its past, that left it in the strange, half-built state astronomers keep finding when they look closely. The question worth asking now is not what Dragonfly 44 is made of, but what kind of history produces an object like this in the first place. Start with what a normal galaxy needs to become the kind of bright, structured object most people picture when they hear the word. It needs gas. Specifically, cold hydrogen gas, dense enough in places to collapse under its own gravity and ignite into stars. Without a steady supply of that gas, star formation slows and eventually stops. A galaxy with little gas left is a galaxy stuck with whatever stars it already has, aging in place, growing dimmer over time as its brightest, hottest stars burn out first. Dragonfly 44 shows exactly this signature. Its stars are old, not scattered, mixed generations the way a young, actively star-forming galaxy would show, but a population that looks like it formed early and then largely stopped. Something removed the raw material this galaxy needed to keep building, and it happened a long time ago. There are a few candidates for what that something could have been, and none of them require anything exotic. Consider what happens inside a young galaxy once its first generation of massive stars finishes burning through their fuel. Those stars do not fade quietly. They end in supernova explosions, violent enough to drive shockwaves through the surrounding gas. In a large, massive galaxy, that gas is held in place by strong gravity, and the explosions simply stir it without expelling it. In a smaller, lower-mass galaxy, the same explosions can do something more drastic. They can push gas clean out of the galaxy entirely, faster than gravity can pull it back in. Picture trying to hold water in a bucket with a wide crack near the bottom, while someone keeps shaking the bucket. A small amount of shaking barely matters if the crack is small and the bucket is heavy enough to stay steady. But shake a lighter, more fragile container hard enough, and water sprays out faster than it can settle back down. A galaxy with a shallow gravitational well is that fragile container. Supernova explosions from its own first generation of stars are the shaking. Once enough gas gets pushed out, there is nothing left to build the next generation of stars from, and the galaxy is left holding only what it managed to form before the gas ran out. This process has a name among the astronomers who study it: feedback-driven gas loss, sometimes described more simply as a galaxy quenching itself from the inside. It is not a fringe idea. It shows up in computer simulations of galaxy formation across a wide range of masses, and it explains, at least in part, why so many small and mid-sized galaxies across the universe look old and gas-poor rather than young and actively forming. But Dragonfly 44 is not small in the way this explanation usually applies. It carries a mass close to the Milky Way's, or somewhere close to it depending on which measurement you trust. A galaxy that massive should have held onto its gas far more easily than the small dwarf galaxies where this kind of self-quenching is most commonly observed. This is where the story runs into a genuine, unresolved tension, and it deserves to be said plainly rather than smoothed over. If Dragonfly 44 really carries Milky Way scale mass, ordinary supernova feedback struggles to explain why it lost so much of its star-forming gas so early. One idea researchers have proposed takes a different angle entirely. Instead of losing gas gradually from internal explosions, Dragonfly 44 may have been robbed of its gas by an external force, stripped away during an early, close encounter with a much larger galaxy or a dense region of the forming Coma Cluster. Gas moving through a dense medium, the hot, diffuse material that fills the space between galaxies in a cluster, experiences a kind of drag, similar to how a swimmer moving through water feels resistance. A person walking through air never does. Think of a sheet hanging on a clothesline in a strong wind. A light sheet gets pulled straight off the line if the wind is strong enough, even while the heavier line itself stays put. A galaxy passing quickly through the dense gas near a cluster's center can lose its own loosely held gas in a similar way, stripped off by the surrounding pressure, while its stars and dark matter, held more tightly by gravity, stay behind. Astronomers call this process ram pressure stripping, and it is well documented in other galaxy clusters, including our own. If something like this happened early in Dragonfly 44's history, it would explain a galaxy that started with the mass and the dark matter halo to become something much larger, only to have its gas supply cut off before that potential was ever reached. Not a small galaxy that stayed small. A galaxy built with the ingredients for something bigger, interrupted partway through. That framing gives Dragonfly 44 a description some researchers have started using seriously: a failed galaxy. Not failed in the sense of being unimportant, but failed in the sense of a structure that had the mass and the dark matter scaffolding to become a full, star-rich galaxy, and simply never got the chance to finish. Most of what makes a galaxy feel significant to us, its brightness, its visible structure, its stars, turns out to be almost incidental to what it actually is underneath. Strip away the stars, and the mass, the shape, the gravitational identity of the galaxy remains almost entirely intact. Dragonfly 44 is not a small thing that stayed small. It may be a large thing that never finished becoming visible. Which raises a much larger question than anything about one galaxy's formation history. If a structure this massive can exist while giving off almost no light, and if more than 1,000 similar objects have already turned up in surveys across the sky, then how many other unfinished galaxies are out there right now, carrying the mass to be something significant, waiting on a supply of gas that may never arrive? That question does not have to stay hypothetical. Astronomers have already gone looking for the answer, and the number they found is larger than most people expect. Since Dragonfly 44 first drew attention in 2016, wide-field sky surveys have turned up more than 1,000 galaxies that share its basic profile. Large in extent, extremely faint, easy to mistake for background noise if you are not specifically looking for them. Consider what that number actually implies about the years before this search began. 1,000 objects this size do not appear out of nowhere the moment someone builds the right instrument. They were sitting in the data the whole time, in images taken by ordinary telescopes for ordinary purposes, unremarked because nobody had a reason to look for something this faint on purpose. Dragonfly 44 did not create a new category of galaxy. It gave astronomers a reason to search their existing archives for a category that had been quietly overlooked. Not every one of these newly cataloged objects turned out to look like Dragonfly 44 underneath the surface. Some of them, when astronomers measured their internal motion the same way Van Dokkum's team measured Dragonfly 44's, showed almost no evidence of hidden mass at all. Their stars moved at speeds consistent with nothing more than the visible material sitting right there in the image. That result surprised people more than a dragonfly-like galaxy would have. A galaxy with almost no visible matter and almost no dark matter either raises a much harder question than one with plenty of hidden mass. If dark matter halos form early, wrapping around the first clumps of gas before galaxies even finish assembling, how does a galaxy end up with almost none? One proposed answer involves violent, close encounters between galaxies. Collisions energetic enough to strip dark matter away from a smaller galaxy's stars, leaving the stars behind in a thin, fragile shell, while the invisible material that once held them together gets torn off and scattered elsewhere. Picture two rivers merging where the currents run at different speeds. Debris caught in the slower current can get left behind entirely, stranded along a bank, while the main flow carries everything else downstream. A near collision between galaxies can do something structurally similar to a smaller galaxy's dark matter, separating it from the stars that used to sit inside it. If the encounter happens at the right speed and the right distance, the stars survive the encounter. The invisible scaffolding that used to hold them does not. So within the same broad category, the same general description of large, faint, low surface brightness galaxies, astronomers found two opposite extremes, some carrying almost nothing but dark matter, like Dragonfly 44, others carrying almost none at all. That range matters enormously, because it rules out the simplest possible explanation for what these galaxies are. This is not one uniform type of object with one uniform formation story. It is a broad category holding at least two very different kinds of history inside it. We think that diversity deserves more attention than it usually gets, because it changes what Dragonfly 44 actually represents in this larger picture. It is not the typical example of its class. It sits at one extreme edge of a spectrum that stretches from galaxies almost entirely made of dark matter to galaxies with almost none. Somewhere in between those two extremes sit galaxies that formed through gas loss, like the ram pressure stripping discussed earlier. Somewhere else sit galaxies shaped by violent near collisions. The category itself turned out to be a mixture of causes, not a single mechanism repeating itself across the sky. A name like ultra-diffuse galaxy sounds like it describes one thing. It describes an appearance, not a shared history. Two objects can look almost identical through a telescope and have arrived at that appearance through completely different physical processes. One built up with too much invisible mass, another stripped down to almost none. Discovering that took years of follow-up work after the initial excitement around Dragonfly 44 had already faded from public attention. There is something quietly humbling in that timeline. The moment that made headlines was the discovery. The part that actually built understanding came later, slower, less dramatic, and mostly invisible to anyone who was not directly reading the astronomy journals where these follow-up studies appeared. 1,000 galaxies is not 1,000 answers. It is 1,000 new questions, each one requiring its own patient measurement before anyone can say with confidence which side of that spectrum it falls on. If appearance alone cannot tell you a galaxy's history, then looking at Dragonfly 44 itself, sitting there in its own patch of the Coma Cluster, what would it actually feel like to stand inside something built this way, carrying all that invisible mass and almost none of the light most galaxies use to announce themselves? Picture standing on a hypothetical surface somewhere inside Dragonfly 44, in whatever spot might function as a viewing platform for something that has no solid ground at all. Look up. What comes back is not black, and it is not the crowded dazzle of the Milky Way's night sky either. It is dimmer than that, thinner. A ceiling with a scattering of pale points on it, spaced apart in a way that feels almost deliberate. That description is not guesswork. It follows directly from what the measurements in this story have already told us. A galaxy giving off roughly 1% of the Milky Way's light, spread across a volume comparable in size, means the stars inside it sit far apart from each other on average. Fewer neighbors, longer gaps of true dark between the points of light that do exist. Anyone standing inside it would look up at a sky with real gaps in it, not the dense band most people associate with a galaxy's interior. 99.99% of Dragonfly 44's mass would be surrounding that hypothetical observer completely, and none of it would show up in that sky at all. Not a glow, not a shimmer, not even a faint discoloration where the invisible material sits thickest. Whatever holds this structure together would be exerting its full gravitational pull while remaining totally undetectable to an eye standing inside it. Think about walking through a strong wind on a still, clear day, one with no dust or debris being kicked up to reveal the air's movement. You would feel the wind pushing against you, real and measurable, and you would have no way to see the thing doing the pushing. Dark matter behaves something like that wind, except at a scale where the wind is gravitational rather than atmospheric, and the surface it is pushing against is every star and every hypothetical observer inside the galaxy at once. You could stand there, feel your own weight pulled by something, and see nothing responsible for it anywhere in your field of view. Wind moves through air by colliding with molecules, transferring momentum through direct physical contact. Dark matter's gravitational pull works through space-time curvature, not contact, and current evidence strongly suggests dark matter particles barely interact with ordinary matter at all beyond that gravitational tug. The comparison explains the experience of an invisible force with a physical effect. It does not explain the mechanism dark matter uses to produce that effect, because nobody has confirmed that mechanism yet. Everything we understand about Dragonfly 44's dark matter comes from watching what it does to things we can see. Stars moving faster than they should, globular clusters orbiting a mass that has no visible source, a galaxy surviving forces that should have torn it apart. We have built an entire, carefully measured picture of something purely from its footprints, without ever once seeing the thing that left them. That is not a small caveat tucked into the science. It is close to the center of what makes Dragonfly 44 worth returning to again and again. Every galaxy carries some amount of unseen mass, but most of them bury that mass under enough visible material that the footprints get harder to isolate cleanly. Dragonfly 44 strips almost all of that visible material away, leaving something closer to a pure set of footprints with almost nothing else in the frame to distract from them. We keep returning to this galaxy in this story not because it is beautiful, and it is not, by most conventional measures, not because it is bright, since it barely registers against the night sky at all. We keep returning to it because it offers something rare in astronomy, a chance to study the footprint almost by itself, with the usual crowd of visible matter mostly cleared out of the way. If we can trace something this precisely through its effects alone, tracking its mass, its shape, its influence on everything around it, at what point does the distinction between seeing something directly and inferring it this thoroughly actually stop mattering? Dragonfly 44 is not the strange exception in this story. It is the extreme case that makes visible something already true of nearly everything physics claims to understand. Once you notice it here, you start noticing it everywhere else too. Take the electron. Every physics class in the country describes it with total confidence, negative charge, specific mass, orbiting a nucleus in a way loosely diagrammed on a chalkboard. Nobody has ever seen an electron directly, the way you see a coin sitting on a table. What physicists actually observe are tracks in a detector, deflections in a magnetic field, patterns of light emitted when electrons jump between energy levels inside an atom. The electron itself has never been photographed, held, or looked at directly by any instrument that exists. And yet nobody treats the electron as speculative. It sits at the foundation of chemistry, electronics, and most of modern technology, built entirely on inference from its effects. The same is true of black holes for most of the last century. Astronomers described them with confidence long before anyone had direct evidence, because stars orbiting an invisible point, moving exactly the way gravity around a massive, compact object predicts, left a signature too specific to explain any other way. Most of what physics knows with confidence was never seen. It was reconstructed, carefully, from effects that only make sense if a specific cause is sitting behind them. The dark matter inside Dragonfly 44 is not an unusual case of scientific guesswork standing in for real evidence. It is an ordinary case of exactly how physics has always worked, applied to an object extreme enough that the pattern becomes hard to miss. Think about a detective working a case with no security footage, no fingerprints in the usual sense, nothing that looks like direct proof in a courtroom drama. What they have instead is a consistent pattern. A door unlocked from the inside. A window left ajar at an angle that only makes sense from one direction. Objects moved in ways that only one specific sequence of events explains cleanly. No single piece of that pattern is proof by itself. Together, they leave very little room for an alternative story. Physics builds its confidence the same way. No single measurement of Dragonfly 44's velocity, on its own, would convince anyone of anything. But velocity dispersion, globular cluster counts, and the constraints from X-ray observations all point in directions that overlap enough to leave the field with a strong, testable case, even without anyone ever isolating a dark matter particle directly. That is not weaker evidence than a direct photograph. It is a different kind of evidence, built from convergence rather than a single decisive image. People sometimes assume that we have never seen it directly means we are not sure it is real. Those two statements are not the same thing. Direct observation is one kind of evidence, useful and satisfying when it is available. Inference from consistent, independently confirmed effects is another kind, and it has produced some of the most reliable knowledge physics has ever built, the existence of atoms for over a century before anyone imaged one, the existence of the Higgs field for decades before a particle collider finally confirmed it directly. This does not mean every inference in science turns out correct. It does not mean dark matter is settled beyond question, and this story has already shown you real, unresolved tension in the data. What it does mean is that the absence of a direct photograph is not, by itself, a weakness unique to dark matter. It is the normal condition under which most of physics has always operated, at scales too small, too distant, or too faint for direct observation to ever be possible. The universe was never going to hand over its structure in a form convenient enough for a photograph. Electrons, atomic nuclei, black holes, and now the invisible scaffolding inside galaxies like Dragonfly 44. All of it required patient, indirect reasoning, built from careful measurement and cross-checked against independent methods before anyone could speak about it with confidence. That is not a story about the limits of human knowledge failing us. It is a story about how far careful inference can actually take you when the direct route is permanently closed off. Which brings the story back to Dragonfly 44 itself, sitting where it has always been, inside one of the most crowded, most violent regions of the nearby universe. Because everything discussed so far, the velocity, the mass, the dark matter, has treated the galaxy almost as if it exists in isolation. It does not. It sits inside the Coma Cluster, surrounded by thousands of other galaxies, all locked together by gravity strong enough to tear weaker structures apart. And understanding what that environment has actually done to Dragonfly 44 over the roughly 10 billion years it has likely existed means looking outward now, past the galaxy itself, into the crowded neighborhood that shaped it. The Coma Cluster is not a quiet place to be a galaxy. It holds somewhere close to 1,000 large galaxies, packed into a region of space small enough, on cosmic terms, that gravitational interactions between them happen constantly rather than as rare events. Dragonfly 44 sits inside that crowd, and everything about its survival so far only makes sense once you understand what that crowd is actually doing to everything inside it. Start with the raw scale of what holds a cluster like this together. The combined mass of 1,000 galaxies is enormous, but even that visible mass is not enough to explain the speeds at which those galaxies move relative to each other. Just as with individual galaxies like Dragonfly 44, clusters themselves show the same signature of hidden mass, only at a far larger scale. The galaxies inside Coma orbit the cluster's center fast enough that something well beyond their combined visible mass has to be holding the whole structure together. It is not one unusual object carrying invisible mass sitting among ordinary neighbors. It is one small, extreme example of a pattern that repeats at every scale astronomers have measured, from a single galaxy up through an entire cluster of them. The invisible scaffolding does not stop at the edge of one galaxy. It appears to extend outward, binding whole clusters together the same way it seems to bind Dragonfly 44's own stars. Inside that larger structure, individual galaxies do not simply drift past each other undisturbed. Close encounters happen. Sometimes two galaxies pass near enough that their gravity distorts each other's shape without a direct collision. Sometimes the passage is close enough to strip material away entirely. And running through the entire cluster, filling the space between galaxies, is something almost never mentioned outside of specialist astronomy. Hot, diffuse gas, heated by the cluster's own gravity to temperatures in the millions of degrees, thin enough that it would register as an excellent vacuum by any standard on Earth, and yet dense enough, across the vast scale of a cluster, to matter enormously for anything moving through it. Picture a swimmer moving through a lap pool compared to someone walking the same distance across dry land. The water resists motion in a way air simply does not. Not because water is heavier in some abstract sense, but because there is more of it in continuous contact with the swimmer's body at any given moment, slowing them down steadily rather than letting them move freely. A galaxy moving through the hot gas filling a cluster experiences something with the same basic logic, resistance proportional to how much gas it has to push through and how fast it is moving. This resistance acts differently on different parts of the galaxy. Gas within the galaxy itself, held loosely compared to its stars, feels that outside push directly. The stars, bound more tightly by gravity to whatever mass sits at the galaxy's center, mostly do not. This returns us to something raised earlier in this story, the process called ram pressure stripping. And inside a real cluster environment like Coma, it is not a rare or occasional event. It is closer to a constant condition, acting continuously on every galaxy that spends enough time moving through the cluster's dense central regions. A galaxy passing near the center at high speed can lose a meaningful fraction of its own gas in a single passage, gas that took billions of years to accumulate, stripped away over a period that might be measured in a few 100 million years or less. If Dragonfly 44 spent time moving through the denser regions of Coma earlier in its history, this offers a second independent path toward the same outcome discussed several acts ago. Not gradual internal quenching from its own supernovae, but active removal from outside, driven by an environment violent enough to strip gas away from a galaxy that never got the chance to hold on to it. Both explanations remain live possibilities. Neither has been ruled out. And it is entirely possible both processes played some role, working together rather than as competing, mutually exclusive stories. There is a detail in this that deserves particular attention because it reframes everything discussed about Dragonfly 44's survival. A galaxy this thin should not have lasted inside an environment this rough. That was the puzzle sitting at the very start of this story, back before anyone had measured its mass at all. Now, with the full picture assembled, that puzzle resolves into something closer to an explanation. The same dark matter halo that gives Dragonfly 44 its extreme mass-to-light ratio is very likely the same thing keeping it intact against the tidal forces of its crowded neighborhood. Without that invisible mass, this galaxy would almost certainly have been torn apart long ago. The same forces that stripped its gas, eventually stripping its remaining stars as well. We think there is something worth sitting with in that connection, because it means the very feature that makes Dragonfly 44 so strange to study is also the reason there is anything left to study at all. Its invisibility and its survival are not two separate facts about this galaxy. They are the same fact, described from two different angles. If a structure this fragile has survived roughly 10 billion years inside one of the most violent gravitational environments nearby, purely because something invisible has been holding it together the entire time, what does that tell us about how much of the visible universe depends on exactly this kind of quiet, undetectable support? Everywhere else we have not yet thought to look closely enough to notice it. Everything measured so far in this story, the velocity, the mass, the gas stripped away by the cluster's hot wind, describes Dragonfly 44 as it existed when the light we are studying actually left it, not as it exists right now. That distinction rarely gets stated plainly, and it deserves to be, because it changes what every measurement in this story is actually telling us. Dragonfly 44 sits roughly 300 million light-years away. That number needs a scale to mean anything, so start here. Light moves fast enough that it crosses the distance between the Sun and the Earth in about 8 minutes. Crossing to the nearest star beyond our own Sun takes a little over 4 years. 300 million light-years is not a small multiple of that distance. It is a distance so large that the light reaching Keck's mirrors right now left Dragonfly 44 before complex life had fully established itself on land here on Earth. Picture a letter mailed a very long time ago, delivered only now, describing a version of the sender that no longer exists in that exact form. The letter is accurate. It describes something real, something that genuinely happened. But by the time you read it, the person who wrote it has aged, moved, changed in ways the letter cannot capture, because the letter only carries what was true the moment it was sent. Every measurement of Dragonfly 44 works the same way. The velocity dispersion, the globular cluster count, the missing X-ray signal, all of it describes a galaxy as it was 300 million years ago. Whatever Dragonfly 44 looks like today, we have no way to check directly. The most recent information we have is already 300 million years out of date. Every image of every galaxy, every star, every distant object studied by any telescope on Earth shows the past. Some of it the recent past, some of it staggeringly old. Astronomers do not observe the universe as it currently exists. They observe layers of history stacked at different distances, each one a snapshot taken at a different point along light's long journey toward us. 300 million years is enough time for a galaxy to change meaningfully. Enough time for it to pass through a dense region of its cluster and lose more gas than it already has. Enough time for a close encounter with a larger neighbor to strip away material we assumed was still there. Whatever debate exists today about Dragonfly 44's true mass, about whether dark matter or modified gravity better explains its motion, that debate is happening using data describing a galaxy whose present state nobody has actually seen. This does not undermine the measurements themselves. The physics used to interpret that ancient light, the Doppler shift, the relationship between velocity and mass, none of that depends on when the light was emitted. A photon carries accurate information about the conditions at the moment it left its source, regardless of how long the journey afterward takes. What it does mean is that every conclusion in this story carries an invisible timestamp, one easy to forget, because nothing about looking through a telescope feels like looking backward in time. It simply feels like looking. We know a great deal about Dragonfly 44's distant past, its motion, its mass, its likely history stretching back nearly 10 billion years. We know almost nothing about its present, the exact moment happening there right now, because that information has not had time to reach us yet and will not for another 300 million years. In a very real sense, the Dragonfly 44 being discussed throughout this entire story is not a place. It is a moment, frozen in transit, still arriving. This changes how you might picture the whole story, if you let it settle for a second before moving forward. Every act in this account, the discovery, the measurements, the debates between research teams, all of it describes something that finished happening long before any of the scientists involved were born. The urgency in their published disagreements, the years spent refining an instrument, the careful correction of an earlier result, all of that very real, very present human effort has been aimed entirely at understanding an event from the deep past, one that continues, in some form, completely out of reach of anyone alive today. The scientists chasing this galaxy's secrets are themselves finite, working within a human lifetime, while the object of their study exists on a timescale that makes a human lifetime nearly impossible to register at all. And that gap, between how long it takes to understand something and how long that something has already existed, raises a different kind of question than anything asked so far in this story. Not what Dragonfly 44 is made of, but what it actually costs a person to spend their working life chasing an answer that light itself will not fully deliver for another 300 million years. Peter von Dockum has spent more than a decade returning to this same faint object in the Coma Cluster. Not because Dragonfly 44 changes dramatically each time he looks, because the tools available to look at it keep improving, and each improvement forces another round of measurement, another round of doubt, another round of publishing a number that might already be wrong by the time the paper goes to print. Consider what that actually asks of a person, professionally. A career in astronomy runs on results, on findings clear enough to build a reputation, secure funding, train the next generation of researchers. Most careers in this field are not built around one object studied obsessively for years. They are built around breadth, moving from one target to the next, publishing steadily, staying visible in a competitive field where telescope time gets awarded to whoever makes the strongest case for why their project deserves it over someone else's. Van Dockum's team chose something closer to the opposite path with Dragonfly 44. Returned to the same faint smudge of light again and again, across 3 separate years, with 3 separate instruments, knowing each new measurement carried real risk of contradicting the one before it. That risk is not abstract. When the 2019 measurement came back lower than the original 2016 result, it did not just refine a number. It handed critics of the dark matter interpretation a specific, citable example to point to, one connected directly to his own name. Picture a bridge inspector who built the original design decades earlier, called back now to test whether that same bridge can hold the load it was rated for. If the newer instruments reveal a weakness the original calculations missed, the inspector faces a choice most people never have to make in their own work. Report the flaw under their own name, publicly, attached to a structure they designed, or stay quiet and let someone else eventually find it. Van Dockum reported it, not once, but as a matter of ongoing practice, treating his own earlier conclusion as something to test rather than something to protect. That kind of intellectual honesty carries a cost most descriptions of scientific discovery skip over entirely. It is easier, reputationally, to let an exciting early result stand unchallenged, especially once it has already been covered by major outlets and folded into the public understanding of dark matter. Revisiting it invites scrutiny most people would rather avoid. Van Dockum invited it anyway, repeatedly, because the alternative, protecting a headline instead of following where the evidence actually led, would have meant doing something closer to advocacy than science. There is a quieter cost here too. 33.5 hours of Deimos observation time, spread across 6 nights, followed years later by 25 more hours on the Keck Cosmic Web Imager. Telescope time at Keck is allocated competitively, often booked more than a year in advance, with far more proposals submitted than nights available. Every hour spent measuring one faint galaxy's velocity is an hour not spent on some other target, some other question, some other astronomer's proposal that did not get approved instead. Multiply that across an entire career built partly around this one persistent question. A finite amount of working life, spent returning to the same uncertain answer, refining it slightly, never quite closing it. Most people, asked to describe what a scientific career looks like from the outside, picture something closer to a single triumphant discovery. What this actually looks like, most of the time, is closer to a long negotiation with uncertainty, one measurement at a time, over years, sometimes over an entire working life. We think there is something acknowledging honestly in that, not to romanticize the difficulty, but because it changes how the earlier parts of this story should sit with you. Every number given so far, the trillion solar masses, the revised figure closer to 160 billion, the missing X-ray signal, arrived only because specific people decided that an uncomfortable, unresolved question deserved more of their limited working years than a comfortable, settled one would have. This is not unique to Dragonfly 44, and it should not be treated as though it is. Every galaxy studied with this kind of care, every dark matter halo mapped, every stellar velocity measured across 6 patient nights of observation, represents the same basic trade a human being made. Time spent on something that might not resolve cleanly within a single career, in exchange for a small, real addition to what anyone can know for certain. There is a specific kind of patience required here that deserves to be named plainly rather than assumed. Not the patience of waiting for something you already know is coming. The patience of working carefully on a question that might still be unresolved when you retire, hand it off instead to whoever picks up the same faint smudge of light a decade or two from now with instruments that do not exist yet. Van Dockum will very likely not live to see this debate settled cleanly, whichever way it eventually resolves. Neither will most of the researchers currently working on it. The reward is not a final answer delivered on a convenient timeline. The reward is a small, real, verifiable piece of understanding, added carefully to a structure other people will keep building long after the person who added it has stopped working on it entirely. Which raises a question that has been building quietly underneath this entire story. If nobody currently alive is likely to see this question resolved cleanly, what does the field actually know for certain right now, today, about Dragonfly 44, separate from everything still under active dispute? Step back now and ask a direct question. After 16 sections of measurement, correction, and disagreement, what does anyone actually know for certain about Dragonfly 44? Not what is suspected, not what one team argues over another. What is actually settled? Start with what nobody disputes. The galaxy exists, roughly 300 million light-years away, inside the Coma Cluster. It gives off a tiny fraction of the light you would expect from something its size, somewhere close to 1% of the Milky Way's brightness. Both the dark matter camp and the modified gravity camp agree on that much, because it comes from direct photometry, measuring the actual light collected, not from any model or interpretation layered on top of it. Also settled, the stars inside Dragonfly 44 are old. Whatever process shaped this galaxy, star formation largely stopped a long time ago, and nobody studying it seriously argues otherwise. The globular cluster count, somewhere close to 90, also holds up as a direct observation, counted rather than inferred. Now for what remains unsettled, and this list matters more than it might first seem, because it defines exactly where the real argument still lives. The precise mass of Dragonfly 44's dark matter halo has 3 different values on the table, depending on which instrument and which year you trust, ranging from close to 1 trillion solar masses down to something considerably smaller. Nobody has reconciled those 3 numbers into one agreed figure. Whether the explanation for its motion requires dark matter at all, or whether it points toward gravity itself behaving differently at very weak accelerations, also remains open. Both explanations have serious researchers behind them, and neither has produced the kind of decisive evidence that would end the argument outright. And the formation history, whether internal supernova feedback pushed the gas out, or whether ram pressure stripping from the cluster environment did it, or some combination of both, remains a genuinely open question, with reasonable physical arguments on more than one side. Here is a way to think about the shape of that uncertainty, because listing 3 open questions in a row can start to sound like the whole picture is unstable, and it is not. Picture a jigsaw puzzle, mostly assembled, with a clear image visible across most of the surface, but a handful of pieces near one edge, still unplaced. You would not say the puzzle tells you nothing. You would say the picture is real and mostly resolved, with specific, identifiable gaps rather than a vague fog covering the whole thing. That is closer to where Dragonfly 44 actually sits. Most of the picture holds. The unresolved pieces are specific and nameable, not a general cloud of doubt over everything. This distinction matters because casual conversations about science tend to collapse it. Either something is fully known, treated as settled fact, or it gets waved off as pure speculation, not really understood at all. Dragonfly 44 sits in neither category. It is a case where careful people, using serious instruments, have converged on most of the picture while genuinely disagreeing about a few specific, well-defined pieces of it. That is not a failure of science. It is closer to what science actually looks like most of the time, on almost every subject, if you look closely enough before the textbooks smooth it over. It would have picked one side, the dark matter explanation or the modified gravity explanation, stated it with total confidence, and left out the tension entirely. That version would sound more satisfying by the end. It would also misrepresent what is actually happening in the field right now, in real time, among people still actively working on this exact galaxy. If you came into this expecting a clean resolution, a final number, a settled verdict on dark matter versus modified gravity, that resolution was never actually available, not because this account failed to find it, but because the field itself has not found it yet. What you got instead is something closer to an accurate map of where the actual boundary between known and unknown currently sits, drawn as precisely as the evidence allows. That boundary will move. It already has. 3 times over the past decade. Each time a new instrument or a new team took another careful look. Dragonfly 44 will very likely look different in this story if it gets told again in another 10 years. Not because anything about the galaxy itself changed, but because the tools pointed at it will have improved again, the way they improved from Van Dokkum's first images to the Keck Cosmic Web Imager's finer resolution. Every open question named in this video is not a dead end. Each one is a specific, addressable target for the next instrument, the next observing run, the next graduate student choosing a thesis topic because a smart, honest disagreement in the published literature caught their attention. Uncertainty like this is not the absence of progress. It is what progress looks like while it is still happening, before anyone gets to write the settled version. If living with an unresolved question like this is simply the normal condition of real scientific work, what does it actually take, personally, to hold that kind of uncertainty without needing it to resolve? What does it actually take to hold an unresolved question without needing it to resolve? Not in the abstract. In practice, day to day, for someone whose actual job depends on saying something concrete about a galaxy that refuses to give a clean answer. Start with something most people outside research never have to face directly: a grant proposal. Every few years, a researcher working on Dragonfly 44 has to write a document explaining what they expect to find, how confident they are in the approach, and why funding this particular observation is a better use of limited telescope time than funding someone else's. That process rewards confidence. Reviewers respond to clear hypotheses, well-defined expected outcomes, a sense that the money will produce a result worth reporting. And the honest answer, for a project like this one, is often closer to, "We don't know what we'll find," and the last 2 attempts change the picture instead of confirming it. That tension is real, and it shapes how a career like this actually gets built. A researcher cannot simply say, the truth is complicated in a funding application and expected to compete well against a proposal promising a cleaner result. So the work of holding uncertainty honestly, in public, in the published record, has to happen alongside a career structure that mostly rewards the opposite instinct. Think about a doctor treating a condition where the standard treatment sometimes works and sometimes does not, and nobody has yet figured out which patients respond to which approach. A doctor in that position cannot simply tell a patient, "We don't know," and stop there. They have to act on the best available evidence while staying honest, internally, about how incomplete that evidence still is. The two things exist together. Confident enough to act, honest enough to keep questioning the action once new evidence arrives. That is close to the position every researcher working on Dragonfly 44 has occupied since the first measurement in 2016. Confident enough to publish a specific number, honest enough to publish a lower one 3 years later, under their own name, when better data demanded it. Neither the confidence nor the honesty cancels the other out. Both are required, at the same time, for the work to mean anything at all. There is a psychological cost to this that rarely gets discussed openly. Humans are not naturally comfortable holding two competing explanations at once without picking a side. Most people, given a choice between dark matter and modified gravity, would eventually feel pressure to commit, to decide which one they believe is probably correct, even without new evidence forcing that decision. Staying genuinely undecided, for years, on a question this central to your own field takes a kind of discipline that goes against normal human instinct. Consider what it means to specialize in a question you might not see resolved in your working lifetime, while still building an entire career, reputation, and sense of purpose around it. That is not the same as simply being patient. Patience implies waiting for something you already expect to arrive eventually. This is closer to something else. A willingness to find the work itself meaningful, separate from whether it ever produces the tidy conclusion a textbook chapter would eventually need. We think there is something naming plainly here, because it changes how the entire disagreement between dark matter and modified gravity should sound to you, the listener, rather than to someone reading a summary in a science magazine years from now. Every voice in that argument, Van Dokkum's team defending a revised but still substantial dark matter estimate, McGaw and other MOND researchers pointing to the same revised numbers as support for their own framework, belongs to a person who has chosen to spend years of their limited working life on a question that might still be unresolved when they retire. Neither side is performing certainty they do not actually feel. That distinction matters. A person defending a position they genuinely believe, based on the evidence in front of them, while openly acknowledging the evidence remains incomplete, is doing something different from a person defending a position simply because they already committed to it publicly. The disagreement over Dragonfly 44 has mostly stayed in the first category. That is rarer in any field than most people assume, and it deserves to be recognized as its own kind of achievement, separate from whichever explanation eventually turns out to be closer to correct. If the researchers themselves can hold this level of uncertainty without needing it resolved, what does it look like for you, listening to all of this from somewhere far outside the field, to do the same? Not to resolve the dark matter question in your own mind before falling asleep tonight. Something quieter than that. To sit with a real unanswered question about the universe and let it stay unanswered without that feeling like a loss. There is a difference between an open question and a question nobody is working on. Dragonfly 44 belongs firmly in the first category, and it helps to know exactly what specific tests are already planned or underway, rather than treating the uncertainty as something drifting indefinitely. Start with the instrument most likely to move this story forward within the next several years. The Vera Rubin Observatory, currently coming online in Chile, was built to do something no previous survey has managed at this scale: photograph the entire visible sky repeatedly, night after night, for a full decade. Most surveys take a single deep image of a patch of sky and move on. Rubin returns to the same regions again and again, building up both depth and a record of anything that changes over time. Here is why that matters specifically for galaxies like Dragonfly 44. Finding one ultra-diffuse galaxy required a custom instrument built out of camera lenses pointed carefully at a known cluster. Rubin will catalog thousands of them automatically, across the entire sky, with a uniformity no single research team could match by hand. That solves a problem this story has touched on more than once. Right now, the roughly 1,000 known ultra-diffuse galaxies almost certainly represent a fraction of how many actually exist. Most surveys before Rubin were not sensitive enough, or not wide enough, to catch the faintest examples consistently. Picture the difference between searching a large field with a flashlight, one narrow beam at a time, and turning on a bank of floodlights that cover the whole area at once. The flashlight approach will eventually find what is out there, but slowly, and it is easy to miss something sitting just outside the beam. Rubin functions closer to the floodlights. Once it has surveyed the full sky several times over, astronomers will have a genuine statistical sample of ultra-diffuse galaxies to work with, not just a scattered handful discovered one at a time by teams who happen to look in the right place. A larger sample changes what questions become answerable. Right now, arguments about Dragonfly 44 rest heavily on this one object because it happens to be one of the most thoroughly studied examples of its kind. With a few thousand similar galaxies cataloged and measured consistently, researchers can ask a different kind of question. Not just, what is going on inside this specific galaxy, but, across the whole population, does the balance of dark matter versus visible matter follow a pattern predictable enough to test one explanation against another cleanly? This is where a second set of tools comes into the story, ones built specifically to test the dark matter versus modified gravity question directly, rather than by inference from galaxy rotation alone. Underground detectors, shielded from cosmic radiation by miles of rock, continue running experiments designed to catch a dark matter particle interacting with ordinary matter, even once. None of them have succeeded yet, but the sensitivity of these detectors keeps improving by roughly an order of magnitude every several years, and physicists working on them are candid about where that leaves the search. Either the particle exists, and current detectors are still not sensitive enough to catch it, or the whole framework needs a fundamental rethink. There is an honest tension naming here, one that runs parallel to everything already covered about Dragonfly 44. If a dark matter particle is eventually caught directly, in a detector somewhere deep underground, that single result would settle far more than any galaxy rotation measurement ever could, because it would move the evidence from indirect inference to direct detection in one step. If decades more pass without a single detection, that absence starts to carry its own weight, the same way the missing X-ray signal around Dragonfly 44 narrowed the range of what its dark matter halo could plausibly be. Neither outcome has happened yet. Both remain live possibilities, and the researchers running these detectors know that as well as anyone. Computer simulations of galaxy formation have grown considerably more detailed over the past decade, modeling how gas, stars, and dark matter interact together as a galaxy forms and evolves. Running a simulation that successfully produces something resembling Dragonfly 44 from initial conditions consistent with the early universe, without simply tuning the model to match the answer already known, would offer a different kind of evidence than any single observation could. It would test whether the formation story proposed for this galaxy, gas loss through internal feedback or external stripping, actually works when you let the physics run forward, rather than reconstruct it backward from what survived. None of these three approaches, wider surveys, particle detectors, and improved simulations, guarantees a clean answer within the next decade. Science rarely offers guarantees on a convenient timeline. What they offer instead is something more useful than false certainty. Specific, well-defined tests, each one capable of narrowing the range of possible answers a little further, even if none of them delivers a final verdict on its own. The unresolved questions named earlier in this account are not questions sitting in permanent limbo. Each one has a path forward already under construction, funded, built, and in some cases already collecting data. The uncertainty in this story is real, and it is also, in a very specific sense, temporary. Not resolved yet, not unresolvable. Everything covered so far has stayed fixed on Dragonfly 44 itself, its mass, its history, the instruments built to study it. There is a different question sitting underneath all of that, one this story has circled several times without asking outright. What does it actually mean for you, listening to all of this from a small, warm, ordinary room? That a galaxy this strange, this far away, took this much careful human effort just to become slightly less mysterious than it was before anyone looked. There is a specific kind of relief that shows up not when a question gets answered, but when you stop needing it to be. That relief rarely gets discussed in science communication, mostly because it sounds like giving up on the truth rather than making peace with how truth actually arrives. Consider what it would mean if Dragonfly 44 had been settled cleanly back in 2016. The original trillion solar mass figure standing forever. Unchallenged, dark matter confirmed beyond argument. That version of the story would feel satisfying to hear once. It would also be false, and false in a way that would have quietly damaged something larger than one galaxy's reputation. It would have taught anyone paying attention that science delivers final answers on a predictable schedule, that uncertainty is a temporary embarrassment rather than a normal condition, that a good result is one that never needs revisiting. None of that is how careful knowledge actually gets built, and Dragonfly 44 has shown you that directly, across 18 sections now, rather than telling you about it in the abstract. A measurement in 2016. A correction in 2019, an X-ray result narrowing the range further still. 3 different numbers, none of them wrong exactly, each one accurate to the limits of what its particular instrument could see at the time it was collected. Think about a photograph developed slowly in a darkroom, the old chemical kind, where an image emerges gradually out of what looks at first like plain gray paper. Early in the process, you can already tell something is forming, shapes beginning to separate from the background, but fine detail stays hidden until the chemistry has had enough time to finish its work. Stop the process too early, and you get a real image, just an incomplete one, true as far as it goes, but missing the parts that would only appear with more time in the developing bath. Dragonfly 44's story has behaved something like that print, developing a little further with each new instrument, each stage genuinely accurate to what could be seen at that moment, none of them the final, fully resolved picture. This distinction matters because it separates 2 very different kinds of not knowing. There is the kind of uncertainty that comes from careless work, from skipping steps, from rushing to a conclusion before the evidence supports it. And there is the kind that comes from doing careful work on a question hard enough that no single measurement could ever finish it alone. Dragonfly 44 belongs entirely to the second category. Every uncertain number in this story arrived because someone measured something real, carefully, with the best tools available at that specific moment, not because anyone cut a corner. An honest disagreement between careful researchers is not a sign that something has gone wrong with science. It is closer to a sign that something has gone right, that the field is still testing its own conclusions rather than protecting them out of habit. Choosing to publish a lower number after your own earlier, more exciting result gets challenged by better data, takes something closer to integrity than most professional fields ever demand of the people working in them. Van Dockum did not have to revisit Dragonfly 44 in 2019. Nobody would have penalized him for letting the original figure stand quietly while he moved on to other projects. He returned anyway, pointed a sharper instrument at his own claim, and reported what came back even though it complicated the story that had already made his name known outside the field. That kind of honesty is rare enough, across any profession, that it deserves recognition on its own terms, separate entirely from whichever explanation eventually turns out closer to correct between dark matter and modified gravity. A person who tells you the truth about an uncomfortable result has given you something more valuable than a person who tells you a comfortable answer they are not fully sure of. Dragonfly 44's entire research history has stayed, consistently, on the honest side of that distinction. This offers something quieter to carry forward than a conclusion about dark matter itself, a way of holding uncertainty that does not feel like failure. Not indifference, and not confusion either. Something closer to a settled comfort with the idea that some questions take longer than one lifetime. One instrument, one clean headline to resolve, and that the honest tracking of that slow process is itself a kind of achievement, independent of when or how it eventually concludes. Think about how differently that sits compared to the instinct most people carry into difficult questions in their own lives. The pressure to decide quickly, to land on an answer and defend it rather than staying genuinely open to revising it as better information arrives. Dragonfly 44's story offers a working model for the alternative. Commit fully to careful examination. Publish what the evidence actually shows, even when it complicates what you said before. Trust that the picture will keep sharpening, slowly, through other hands and other instruments, long after your own part in it has finished. None of this resolves whether Dragonfly 44 is 99.99% dark matter or something closer to a Milky Way scale dwarf with an unusually generous halo, or whether the whole discrepancy points toward gravity itself needing revision at its weakest edge. That question remains exactly where it was at the end of the last section, open, actively studied, moving closer to resolution but not there yet. What has changed is not the science. It is the frame you might now be holding it in. Not a mystery waiting to be solved before you can rest easy with it. A living question, cared for honestly by people who will not see it finished, handed forward the way careful work always gets handed forward, incomplete but genuine, real as far as it goes. Which brings this account back, finally, to something much closer than 300 million light-years away. Because everything discussed across 19 sections now, the mass, the light, the instruments, the honest uncertainty, has been building toward one last connection. Not a fact about a galaxy. A fact about what it means to lie here, now, quiet, aware that something this strange exists, and that not needing it fully explained tonight is not a failure of understanding at all. 300 million years is a strange number to hold on to right before falling asleep, so let's bring it down to something smaller first. Every atom in your body, older than hydrogen and helium, was forged inside a star that lived, burned through its fuel, and died long before our solar system existed. You are not separate from the kind of process this whole story has been describing. You are made from the aftermath of it. It is a direct physical fact, the same kind of fact that let Peter van Dokkum measure starlight shifting across a spectrum and call it evidence rather than guesswork. Iron in your blood, calcium in your bones, oxygen in every breath you have taken tonight, all of it built inside stars, scattered by their deaths, gathered again by gravity into a planet, and eventually into you. Dragonfly 44 is made of the same basic ingredients, arranged very differently. Old stars, a thin scattering of visible matter, and, if the measurements hold up, an enormous quantity of something we still cannot name with confidence, holding the whole structure together from somewhere we cannot point to directly. You share the visible half of that description completely. The invisible half remains a genuine open question for that galaxy and, in certain ways, for the universe you are lying in right now. Think about what it actually means to know this much about an object you will never visit, Never photograph directly. Never confirm with your own eyes. 90 hours of instrument time across 3 different telescopes. A team willing to publish a correction to their own earlier work. A separate team pointing X-ray detectors at empty space just to measure what wasn't there. None of that effort was required to happen. Somebody chose to spend a portion of their working life on a question this specific, this far away, this unlikely to ever touch daily life in any practical sense. And yet here you are, hearing about it, on an ordinary night, in an ordinary room, because that effort eventually reached you anyway. That is worth noticing plainly, not as a lesson, just as something true. Careful attention paid to something distant and difficult does not stay contained to the people who did the work. It travels. It reaches rooms like this one, years later, carried by nothing more complicated than someone deciding the story deserved to be told accurately. There is a specific kind of quiet that settles in once you stop needing every question answered before you can rest. Dragonfly 44's mass is still disputed. Whether dark matter or a modified law of gravity better explains, its motion is still genuinely unresolved. Its formation history still has more than one plausible account competing for the same evidence. None of that changes tonight. None of it needs to. You do not have to resolve the disagreement between dark matter and modified gravity to fall asleep tonight. You do not have to decide which of the 3 mass estimates is closest to correct. The universe was going to keep existing in its unresolved state, whether or not you understood it fully, and that fact, instead of feeling like a loss, can simply sit there as something true. A vast structure, working exactly as it works, entirely indifferent to whether tonight is the night you finally understand it. You are not required to hold the whole picture in your mind before you can close your eyes. Van Dockum does not hold the whole picture either, after more than a decade of careful work. Nobody currently alive does. That is not a failure belonging to you, or to him, or to anyone else who has looked closely at this galaxy. It is simply the honest size of the question next to the honest size of a single human working life. What you carry forward from tonight does not need to be a fact you can recite tomorrow. It can be smaller than that, and still real. A sense that somewhere out past easy sight, past the reach of an ordinary backyard telescope, there is a structure roughly the size of our own galaxy, giving off almost no light, held together by something nobody has ever directly touched. And that structure has been sitting there, doing exactly what it does, for longer than anything on Earth has existed to notice it. You do not need to solve that. You only needed to hear it clearly enough, once, to let it become part of how you picture the dark when you close your eyes tonight. Not an empty dark. Not a frightening one either. A dark that turns out, every time anyone looks closely enough, to be carrying more than it first appears to. Thank you for spending these hours with this story, and for trusting a strange, faint galaxy enough to follow it all the way to the end. Sleep well.